what is the area of a circle with radius of? That is an easy question.
Square.
Pi r squared, okay. R here, R there. If we take quarter of a pi, what is the area of quarter of pi? Your Thanksgiving pi. Circle. What? Divide that by 4, you end up getting pi r squared over 4. What is the angle that we have here? 90 degrees. There's also pi over 2. If we want to know what portion of the entire 2 pi revolution we have, I could simply write this as pi over 2 over 2 pi, correct? But if you flip and multiply pi over 2 times 2 times pi, yes, those 2 would go away. So pi over 2 is simply a fourth of 2 pi. Yes. And you might wonder, why do we have to do it this way? Well, I did it for pi over 2. What if you had an arbitrary angle of 32.1983? It's not that easy. So for any arbitrary angle, if you want to know what portion of that circle you covered, it is simply beta divided by 2 pi. Yes, no, maybe.
Explain that one more time.
So until we get this far. So that is a fourth of the entire 2 pi revolution. Good. Pi over 2 is a fourth of 2 pi. So I took the angle divided by 2 pi, part of 2 pi, to get that 1/4. Instead of 90 degrees, let's just say you had an angle of 32.91 degrees, right? And I asked you, well, what portion of 2 pi is that 32.91 degrees? You wouldn't be able to tell me. Agree? But if I have that general formula, all I have to do is put in 32.91 degrees in radians, so times pi over 180, correct? Yes, divide by 2 pi, what do you get? Do you have your calculator for us? .09, so approximately 0.1, right?
Yeah.
So 10% of the whole pi. Agree. So quarter of the pi, about 10% of the whole pi, a third of that quarter, 1/12. So if you want to know what portion that has a name from calculus 1, starts with the letter, or pre-calculus, starts with the letter S, ends with R. rhymes with the person's name, Hector.
Vector.
Sector.
Vector doesn't start with S, Megan.
Oh, I didn't hear that part.
Sector, right? If we want to know the area of that sector, first we want to know what angle or does it span? Well, it is theta divided by 2 pi. If theta is pi over 2, it's a quarter or full 2 pi. So that is the standard expression. Now, if you want to know, well, what portion of the area it covered, well, it's pretty easy. We'll have theta over 2 pi times area of a circle, which is pi r squared. Agree? Pi would go away. I'd simply have r squared times theta 1 over 2. Area of the sector spanned by an angle of theta. Yes, if theta is pi over 2, 90 degrees, pi over 2 will give you pi r squared over 4. Yes, isn't that what we had earlier? Yes, if theta is just pi, you would get pi r squared over 2, which is the area of a semicircle. Agreed? Good so far? So what this gives us is the angle of that sector. In other words, what portion of 2 pi did we cover by moving from the initial side, or theta over 2 pi, multiply that portion by the total area of the circle, I get what portion of the circle's area you get from that sector. Yes? With me so far? Great. You might wonder, well, why did we even bother doing this? Well, we are dealing with polar curves. Circle is the fundamental polar curve that we know. And instead of a nice circle, I have that. Good. Now I want to know the area of that bit. Before going to the break, I said, look at your pie dish, the edge of your pie dish, and think of calculus 2. Did we think of calculus 2? Absolutely not. What a shame. The edge, the corrugated edge. Would the area be the same? Would it be less? Would it be more? No clue. Caleb, you have a look.
I'm not sure what the question was.
The area, instead of the blue line, which is the circle, I used this formula theta over 2 pi to get the angle of the sector, multiplied it by pi r squared, got the area of the sector. My question is, if I change that blue line to a wiggly red line, would the area be the same or will it change? Sharon,
I think not.
you think not? Why not?
I'm thinking of the pie, so when the pie is the crust part, I think the pie will still be circular, so the area will be circular the same.
Okay. Exactly the same?
Well, a little bit different.
Slightly different. Well, in a rough way, one can say, well, I'm taking some off here, adding some there, taking some away, adding, take, add, things sort of balance out, right? Approximately, it is going to be the same. Good? Okay. weird looking pie. I want to know the area. Will it be the same? Huh? No, it is not going to be the same area, it is going to be higher. Let's see. How do we find the area in that case where you have a red boundary instead of the blue one? Can I, yes,
Instead of R, would it be F of R?
so close. Instead of R, will it be F of R? Very close, right? Good thinking. I'll give you a hint. For the curve, what changes as you change theta, right? It is a function of theta. If you look at a circle, no matter where you go, the radius is the same, yes? But if you look at that red curve, is the radius the same as you move along that curve? No, fine. I could use the same logic that I used with a circle to find the area. Do you agree? Provided I know what R is or how R changes with respect to theta. Agreed? So, erase. I have some curve zoomed version. Oh, that looks like a slice of pizza. Theta, right? Some part of 2 pi, and I have 1/2 r squared theta. That's what we know. But when we move from the initial side over to some angle, I am sweeping across the values of theta. That's just how polar curves work. Do we agree? The parameter in polar coordinates is theta. You move theta. So let's say theta, we'll call it theta 1, theta 2. What is the change in angle? Okay, very good. Theta 2 minus theta 1. How do we denote the change in angle? What? How do we denote change in x?
Delta.
Delta x. Change in y.
Delta Y.
Change in theta. How about delta theta? Right? Okay, so that is a tiny sector here. Another sector, yes. Another. If every single one of them delta theta. Good. I know if R is a function of theta, which it is for the curve, R equals f of theta. Area of the sector is 1/2 function of theta squared multiplied by the angle covered by that sector. Yes, which is theta. With me so far? What is the angle covered by each of those sectors? Change in theta? Okay, delta theta. Good. How many pieces do I have? 1, 2, 3, 4, 5, 6, 7 pieces. I need to know essential value for each of them. Let's forget about too many details, and I'm going to put I there, put I there. Good. The ith sector will have the radius defined over there by that function multiplied by the change in theta I, or change in theta. With me so far? Okay. I've used 7 slices. Could I use 4? Okay, how many more? Infinite. If I use infinitely many sectors, do you think I'll get the exact area of that weird shape? Yes, no, maybe? So, that area, I'm going to write it this way. Good. As long as I know the radius function that changes with respect to theta, that I can suitably choose delta theta, and then put it in that formula, which comes from the area of the sector, to find that area. Do you agree? Yes? Gone all the way up to infinity. So perhaps there has to be a different notation. So why not put that n undo limit n approaches infinity? What does that remind you of? Oh, better remind you of calculus, or else it would be a shame. What in calculus?
Headaches.
Pain.
Headaches.
Headaches?
Pain.
Pain?
Pain and suffering.
Okay. Hint, come on, man.
Rain. Sun.
Louder, Caleb.
Raymond Sun.
See, he gets my bad jokes. One person. Louder.
Raymond Sun.
Riemann sum, right? That is nothing but the Riemann sum of each of those areas. So, in short, if you know the radius function, the radius, how it changes with respect to theta, you can find the area of that polar curve. Can I erase? Integral 1/2, some starting point, some ending point, so theta 1 to theta 2, f of theta, which is our function for the radius. Delta theta I becomes d theta y d theta. It is an infinitesimally small change in theta. Yes, so the formula here defines the area of a polar curve. It's just that. You don't have to memorize this. You understand what happened over here. Common mistake. When we do area in rectangular system, when we find the integral, what area are we finding? That's an easy question. Calculus 1, when you found the area using an integral, what area did you find? Louder.
Under the curve.
Area under the curve. Yes? So I erased it. Did I find area under the curve here? No, I've rather found the area
Slice.
of each slice. In other words, the area swept by the angular move that you made. Good. So you're not finding the area under the curve, rather you're finding the area swept about an angle starting from 0 up to, another angle or somewhere in the middle. So if we have a circle start at 0, you go all the way up to pi over 2. The angle that is swept is pi over 2. The area, we did it earlier, it is a fourth of pi r squared. We can't do the same thing for funny looking curves, such as the one that I drew over here, but if we extend that idea, as long as I have a function r, in other words, as to how the radius changes with respect to theta, I can find the area easily. Does that make sense? Good. Okay. I did the common sense approach. Now I gave you this formula. Before we get into something complicated, I'm going to find the area of a circle using that expression that we have. Okay, I'm going to start at 0. You pick. Should we go up to 90, 180, or 270?
180.
180. Okay, which would mean pi. So half the area of a circle, in other words, area of a semicircle, it should be pi r squared divided by 2. Agreed? Okay. The radius of the circle here is just r, so I'm going to put r squared. Nothing changes. Yes? Times d theta. I'm integrating with respect to theta, so r is a constant. In this case, 1/2 r squared integral 0 to pi d theta. What is the integral of d theta? Theta. Upper limit minus lower limit is pi minus 0, which is pi r squared over 2. Isn't that what we have? Yes, no, maybe. Does that make sense?